Recording. I'm going to stop sharing. I'm going to keep the chat open. Gloria. Hey, I'd like to introduce Gloria Fonseca Alvarez. She's going to be leading you through this morning's session.
Okay, it takes me a second to figure out how to actually
Yeah.
share slides, even though I do it all the time. Um, okay. Okay, I don't see presenter mode. So I'll just
Is
leave
it
it.
not under view? And then there's like a slideshow. What?
Yeah, I don't have uh
Or, oh, Safari. Yeah. I don't know.
okay.
Usually there's a bar also that you can say, but maybe show stat. Mm,
Okay.
well, it does look fine like this. So, yeah,
Yeah.
let's go with that.
Okay.
Okay.
Um, okay. So, hi everyone. I'm going to be talking about visit images and the force source table. Um, Welcome to day 2 of the Data Academy. Uh, if you just joined, we also have a parallel session on the Data Preview 1 overview. So if you're completely new and you just really want to, know what is the DP1, we'll also have this visit image and source tables session many times, like a few more times. So if you want to learn about that, you can join the breakout room. And then right after this, we'll have the session on deep coads and the object table, which will also be very useful to get some more context for this session. Um, and hold on, let me open the chat. Okay. Now, we right here in the Data Academy, there are Rubin staff that are here to help you. But if throughout you're working with DP1, you have any other questions, we suggest that you go to community.lsst.org, the community forum, where you can post your questions and get answers from both Rubin staff, but also your fellow community members. And this allows other people to also that may have the same question get answers and maybe start some discussion. So you can post uh, questions in the support category, but there's also many other categories like science. So we'll be talking about the DP1, which just came out yesterday. All of the documentation for the DP1 is on dp1.lsst.io. There's also an upcoming paper on Rubin's Data Preview 1. There is currently a draft, and you can find that in RTN 0995, and this just includes a link to that. And we ask that if you use this data set, that you use the relevant DOI, which you can find in the documentation. But today we'll be talking a little bit about how the visit images and the source tables are processed. And then we'll talk a bit also about what exactly are these data products. And then I'll do a couple of tutorials, first with the portal, and then I'll go through one of the notebooks that we have. Some key concepts, like what is exactly a visit? So a visit is a single observation. All of the exposures in the DP1 were 30-second exposures. Uh, all this data was taken with the LSST commissioning camera, LSST ComCam. Uh, this has only 9 CCDs, so it's not the entire field of view that you would get from LSST cam. Um, so a visit image is just the process image for a single detector in the visit. This right here just tells you some information about how you could possibly access the visit table, which contains information, more specific information about the actual visit that produced the image. So for that, you could access it via the Butler, which is a way to retrieve data. Then you have you could also access it via TAP, and they have different names for the table. Now the visit table has 16 columns and 1,786 rows. So that should tell you that there are that many visits included in the DP1. And there's also a CCD visit table, which contains information also about the specific detectors for the visit. So there's some specific names that we use for things. So a source within the context of LSST is a detection in a process visit image, which is what we're covering today. And then you have an object, which is a specific astrophysical object at a specific coordinate. We have two tables that are related to each other. The source table, which contains all the measurements in each individual image, and then you have the object table, which has measurements that are in the deep coads, which are just the combined process visit images. And then you also have force photometry, where if things were detected in the object, if things are included in the object table, you'll go back and do force photometry in all the individual images. Now, as you may know, all of this data is already processed for you, and it starts with image calibration. So some of the things that are included are instrument signature removal, background subtraction, and then some calibration. The instrument signature removal has corrections for detector effects. This includes biases, flats. It also has the actual sky background subtracted. And then you have both astrometric and photometric calibration. And then we also do, PSF estimation. And then from that, you get visit images, and that is one per detector per visit. And we give you the actual, like the fluxes in nanojanskis. Now, after we get the visit images, we do source detection. Now, a detection would be if something is actually detected at a signal to noise ratio greater than five, than 5 in a visit image. And then we also do deblending. So this on the right is just showing, for example, a source that would be blended and then deblended into two sources. But for this, we measure PSF Gaussian and aperture fluxes, and you also get center shape and size measurements. And you combine that all together, and you get the source table. Now, there's also photometry in the force source table. So once you have, so you do the visit images and you do detections in the visit images, and then you associate all of the different detections in the different images and you assign them an object, and then you go back if something for something that has been assigned to be an object, you go back in every visit image and do force photometry at that location, even if it wasn't originally detected at a signal to noise ratio of 5. Now for this, you do only get PSF flux, but all of that information can be found in the force source table. And this will be a really useful table if you're interested in, for example, variability. Now this just tells you sort of like how to access the visit images and what you get. So the preferred method to access images is via the Butler, but you can also access it via simple image access and also through the TAP. And so for that, for the Butler, you have to tell it what kind of data set it is. For visit images, it's just visit underscore image. And this tells you what information you need in order to access that image via the Butler. And it says there are around 16,000 images. You also get, you get different types of data for the image. You have the image itself, and then you get a variance plane, and then you have a bunch of masks, similar to the SDSS bitmask. And then you also have a bunch of metadata. For the source table, the preferred method to access that is actually the Table Access Protocol tab, but you can also access it via the Butler. So the dataset type for the source table and the Butler is source, and this is the information that you would need for that. But we'll cover that in the notebook tutorial. And then all of the different tables in the DP1 are labeled DP1 dot name of the table. So this would be DP1 dot source. And here are some of the key columns. You have your source ID, which is for every individual source. Then you have visit info, which detector the image was taken in, and what band. You get coordinates, fluxes, and then for the for source table, the name is object for source table, and dp1.force source for the tab. And then for that, you also get an object ID. So the source table does not is like all the individual sources. They'll have like the same array and deck, but you can't easily find all of the sources that are like, for example, like that might be the same actual physical object. So that's why the for source table is better for light curve, since you can just be like, okay, give me all of the information for all the visit images for the same object. But yeah. And then you get both PSF flux and PSF diff flux, since the force photometry is done both on direct and difference images. Okay, so I'll pause here. I think questions have been answered, but if anyone has any questions specifically about the things that I talked about in the slides, please put it in the chat or raise your hand. So now I'm gonna show you how to actually get images, and I'll do that. Oh, am I sharing the RSP?
Yeah, we see it.
Oh, there. Okay. Wasn't sure if I was sharing a desktop or like the specific. But okay. So we'll be oh, I'm sorry, I didn't post the slides. Somebody post the slides.
If you want to go ahead, I can go and grab them and post the link.
I have it. Okay.
Good.
So we'll be using the Rubin Science platform to access the data. You do need to have an account already, but if you don't, you can request it, but you can just follow, like just look at one day. But if you go to data.lsst.cloud, that is the Rubin Science platform, and you'll see that there are different ways to interact with the data. There's the portal, which is good for data discovery. There are notebooks, which is good for actual like analysis, and then there are APIs, so you can programmatically access the data. But I'm going to talk about the portal first. Okay, so if you click, and you'll have to sign in probably. I was already signed in, I think. Okay, I was not signed in. That's why it broke. So you click on login, and I usually sign in via GitHub, but I just wanted to demonstrate the actual sign-in process. Okay, now you can see that I'm actually logged in, and now it will actually go to the portal. But so when you get to the portal, you'll see that there are different tabs here. So you can retrieve images, but you can also retrieve catalogs. And the portal is great because you don't have to actually do any programming. You can just come here and like click around, see maybe what information you might already have. And you can also just give it some coordinates. But so for the images, you'll need to say what kind of image you want. So you'll have access to raw images. And then the visit images are called process visit images. So it will be here calibration level 2. And if you wanted to get the co-added visit images or difference images, which are the images with a template subtracted, you will click number 3. But here you would be, if you wanted to get the visit images, just click here. And you can also see all of the different dataset types that are available. And you'll see that these are actually the same names as the Butler. But you would also be able to just give it a coordinate and do, yeah, so just give it a coordinate. But for to make it easier, I will paste a ADQL query. What are settings 0 and 4? I do not know the answer to that.
They're unused settings that are not supposed to appear there, that there's some kind of a bug that so really only 1, 2, 3 are meant to appear. So
Okay.
they'll probably go away soon.
But you can also, well, you can very easily just like click on the columns that you want. You can also give it an ADQL query, and I will paste it in the chat, and you can also find it in the slides. But here I'm just going to query for a visit image. So here you have to give it the data product subtype, lsst.visit image. And I'm going to, and you also have to tell it the calibration level. And yeah, so I'm just here grabbing a bunch of columns, like the band, this information, is not necessarily relevant. But you'll also see like what visit the image was taken in. But you can just copy and paste this query and then click search. And then that will go to the results tab in the top. And then you get an actual image. Yay. So the default view here is the data product on the left, and then you can make plots in this active chart. And then you have the table, which actually tells you information about the images. So here, all of the images have the data product type visit image, and the calibration label is 2. And it also tells you what band the image is in. So all the different images will be are per band. So here it's the way that it's sorted is you're showing the, oh, did I ask for the R band? I don't think so. But you can like look for okay, I guess this query was just for the R. But you can look at what the specific visit was, and you can like sort by visit, and you can click on the different visit images. So there are cool ways to interact with the image. You can like change the actual like scaling of the image. I'm gonna change it to this. And that should change what the image looks like. If you have like some coordinates that you are interested in, you can go in and mark the position of that. I'm just picking some random part of the image here, but you would probably have something interesting to look at if you're looking for an image here. But you can go and mark, and that will put a little circle in the coordinates that you selected. But you can also look at all the different images together. Is there a way to manually adjust the brightness scaling in the viewer? Currently there's Z scale. Yeah, you can change, I think color stretch. and you can select what the stretch type is and like actually give it some specific numbers. But it also has some like predetermined ones. But yeah, you can. Is that crosshair to corresponding? Yeah, so there's two. There's usually one wherever the actual search coordinates were, and then I put one on some coordinates. And you can also change the color for those. So if you have if you're like if you're selecting many coordinates, you can go and like change what the symbol is, and you can also change the color. Yeah. And you can also, well, you're interested in the images here, you can also click on coverage. And that sort of that shows you all the different observations that we have. So if you want it, I thought it was cool to just like click through the different visits and see like actually like the telescope pointings. But you don't have to do that. Okay. So when the flux is negative, is that because the the source is saturated? Do you see? Oh, because background is obstructed. Okay. Okay, so now I'm also going to do another query. So for example, if you found a particular visit that you wanted to see what actually was detected in the visit, like which of these points was actually detected as a source, you would note the number of the visit, and you could do another query to query the actual source table. So for that, you have to go to the DP1 catalogs, and you can also edit ADQL, and this is a much shorter query. So here I'm selecting all the things in the R band in a specific detector for a specific visit. And here I would be interested in what the flux was. So here in the table is all the different results for that specific query for the source table. So here you could sort by visit, I guess, but they're all the same visit. But yeah, so one cool thing that you can do is, so this just shows you the actual, like this put a little square over all of the different detections. So you could like zoom in, and like if you click on any specific thing, it will also highlight the table. So you can see, hey, this looks like an interesting source. What is the flux? But yeah, and you can also make different plots. But you'll notice that there's no actual date information for the source table. So you would, if you wanted to make a light curve here, you would have to do a join with the visit table, which actually has the date information. But that is all I had for the portal. Hopefully you will at some point explore more in the portal. But yes, okay. Now I'm gonna go back to data.lsst.cloud since we're gonna be looking at the notebooks next. So to actually do analysis, we recommend that you use the notebook aspect. And if this is your first time signing in, you'll see that there are different different versions of the pipelines that you can use, you should select the recommended release. And there are two options for the container size, either small or large. But for this, we're using a large container. Now, when you actually get into the notebook aspect, you get this really cool landing page, which gives you links to the Data Preview 1 documentation and also the community forum, which I mentioned earlier. But in order to access the many tutorials that the community science team put together, you can go to the tutorial tab. And here in the DP1, we have different categories, like how to use the RSP tool. So these are good for like, if you're just looking for information, how to do it like a very specific thing. We're going to be talking about the data products in this section, but there are also science demos for your particular science case. So here for the visit images and related catalog, for the visit images, there's a visit image tutorial, and then the related catalogs would be the source table and the for source table. So we're going to talk about the for source table here. So if you click on that, if you've already opened this at any particular notebook, it will ask you if you want to overwrite. But if you've never opened that before, it will just open. Okay. So all of our notebooks have here what the container size that we recommend, what is the science pipeline versions that we use, and when it was last verified to work properly. So the learning objective for this notebook is to understand the contents of the for source table and how to access those contents. We'll be looking only at the for source, but many of our tutorials look at different data products. And we'll be using two packages, the lsst.rsp and the Butler. And this was originally created by the Bruin Community Science team. But yeah, so the for source contains force PSF measurements on both individual images and the difference images at the coordinates of all objects. So there's a similar table for source on DIA, which is at the coordinates of DIA objects, and that will be covered in one of the sessions tomorrow. But the objects are all of the sources that were detected in the DeepCOAD or in any individual visit. So even if it was only detected one time in an individual visit, it will be an object, and you can find it in the object table. We recommend that you use the for source or the difference image analysis DIA tables for light curves, and rather than the source table. The tab name for the for source is dp1.forSource, and the Butler name is object for source. This table has 28 columns and 270 million rows. So this is like for each individual visit image, and also for each individual difference image, there will be a row. If you want to learn more about the TAP or the Butler, you can look at our 100 level tutorials on how to. And there are also other related tutorials like the visit image, the difference image, and the object table tutorial. So the first thing that we do in all of our tutorials is import some packages. There are the ones that I mentioned before, the lsst.rsp, the Butler, and some plotting tools. Yumi, yes. Oh,
Zoom in a little bit.
Yeah, sorry. Zoom in. Is that good? I will assume that this is now visible. But yeah, so you can just import these plotting LSST.utils plotting tools, which will allow you to get some standard colors and like symbols for the different filters. But we also import, like commonly used packages like NumPy and Matplotlib. And if you've never used a Jupyter Notebook to actually execute the cell, you do Shift Enter. Okay. So one of the first things that we do is create an instance of the tab service, which we will use to query the table. So for that you do service equals get tab service. And we'll also be using the butler, and this is how you set up the butler. So there'll be like different collections in the future. For this is the LSST ComCam DP1. And then we define what the filters are and like I said, color, symbols, and line styles. Now the first thing in this notebook is to look at the table schema. So we can look at what columns are included in the four-source table. And for that, we just get column names, data set type, and the description for the column from the tab schema for specifically the four-source table. So here we typically we'll like save a query and then submit it as a service asynchronously. So if you have a really big query, it will not say completed like right away, but it's recommended that you submit it that way so that you can continue working on your notebook if you have like a long query. And that once that shows as completed, you can fetch the results and then convert it to a table. And then here we're showing the results. But there are 28 columns, and this just lists all of the different names and what their description is. You see here, there's bands, there's coordinates, detector, there's the different fluxes, and then the PSF flux. Yeah. So if you wanted to explore the column some more, you can uncomment these. But once you're done with the query, you can just delete it and also delete the job itself. But while there are 28 columns in the table, there are a few that are commonly used, like for example, the object ID, which tells you, which is a good way to link back to the object table, which will have photometry from the deep coads. There are also coordinates. You'll notice in the different tables that exist, some of the coordinates might have different names. For the four-source table, the coordinates are given in cord_RA and _dec. And you also would probably be interested in what band was used or the visit and which detector. And then one of the most useful columns here would be the actual fluxes, which again are given for both visit images and difference images. And the ones on the visit image are given as PSF flux, and the ones on the difference images are given as PSF diff flux. One note, so the ones on the difference images can be negative just because, sources might be either, there's the template and in other times in the images, it might be brighter or fainter than it was in the template. So if it's fainter than the template, it will give you a negative flux. So it's not recommended that you try to do magnitudes for the different fluxes. But yeah, and then there's different flags, like for example, if any pixels are saturated or if there's cosmic rays. But for this query is just showing you for like the most commonly used, the description for all the most commonly used columns. So if you wanted to write a basic query for the four-source table, you would probably use these columns. But you can also just delete that. Now, the DP1 is a a relatively small data set, but in the future there will be a lot of data. So we do ask that you avoid querying the whole table. So there are different ways that you can make your query more efficient. There are different cases, like if you wanted to if you've identified an object of interest and you wanted to return all of the photometry for that specific object, you can query first the object table to get an object ID and then get all of the photometry for that specific object ID. Or if you wanted to look at a specific visit and a visit image, you could query the visit table, and then get the visit that you want, and then combine that with, and then retrieve all of the photometry for that specific image using the visit. But you can also use table joins. So please do try to write efficient queries. So the first way that I'm going to show you how to access the FORSource table is using the table access protocol. So here there are many variable objects in the DP1. There is an interesting variable start at these coordinates here in Carling et al. 2025 in prep. So the first thing that you wanted to do, if you have the coordinates for a target of interest, is to get the object ID. So here in this query, we are querying the object table here at dp1.object and getting object ID and coordinates, and we're doing a query around those coordinates of 2 arcseconds. So that was completed. And there's only one result, which is good. Okay. So that would give you the object ID for that particular star. And that just tells you again, like what coordinates you used. So now that you have the object ID, you can go and get the photometry from the FORSource table. So here from the FORSource table, you can get object ID, the band, visit, detectors, and both types of fluxes that are given. And you want to get that from the FORSource table. And you want to only give results that have the object ID that we stored before. And okay, this is just a little printout of the query. You can then retrieve the results, and there were 219 photometric measurements for that. So one thing that you can do is to try to get what the mean flux or the minimum flux and standard deviation for each different band. So this just lists in each different filter the number of visits, what the minimum flux, the mean flux, the maximum flux, and the standard deviation. And you'll notice that the different filters have varying numbers of visits. So somebody is having trouble seeing the DP1 Jupyter notebooks. They should already be there. Okay. I think I had already deleted that. I got distracted, sorry. Okay, so you can also join the FORSource table with the visit table in order to actually make something like a light curve, since all of the date information is stored in the visit table. Okay, so here you are from the you would select like your sort of like your first table here. It's a FORSource table, and you want to join the visit table using the the like specific visits. So both for source and visit have, and the visit table have a column for visit. And then here you're also joining on the specific object ID. That is still also very task query. And you can also display results here. And here you'll see that all of the different four sources have the same coordinates and the same object ID, but they have different visits. And then you have also the flux information, different flux, and here the date that we got from the visit table. Okay. Now, once you have that information, you can just plot it here in this particular cell. We're plotting both the PSF flux versus MJD and the different flux versus MJD. And also from the, I believe from the object table, there are the sort of like the fluxes from the co-added images. So you have both time domain and static information in these. But you'll see that this is actually a variable, which has also specifically been determined to be a star in a different notebooks. But yes. So you'll see here on the right that if you use PSF diff, the fluxes will be negative for some of the measurements. But okay, and I am running out of time, so I'm gonna go a bit quicker for the last bit, which is accessing that same table using the butler. So here, I showed in the slides sort of like that you need specific information in order to retrieve it from the butler. You need to know a SkyMap, tract, and patch, or it will tell you all the different things that you can give it. But if you want to know exactly what is the minimum amount of information that I can give it, you can just click, you can write that dimensions that required, and you'll see that you actually do need all of those three things. But you can do a butler query using a spatial constraint. So if you define your array and deck, you can find a region that overlaps those coordinates. And then you'll see that there's actually various different patches that overlap that specific point, and they're in different tracks. But you can just select like specific patches that you'll be interested in. But there are other tutorials that show you how to best determine which patch and track to use. But you want to retrieve some columns, like some of the most commonly used columns. And in order to do so this tells you sort of like the reference to how to get the table. Butler.get is how you actually get the actual table. But here telling it to get the butler results for this specific reference, and only getting the columns that I defined here. Okay, so a question, are the tap and butler equivalent? So the butler is recommended for images, since it makes it easier to grab images without having like too much information about the image. The tap is better for querying the tables. But you should in the end get the same table. But here you're just seeing again like the so different. So this was not for any specific object ID. So you'll see that there's different object IDs, what their array index are, and the fluxes.
Can I add to that question of tap versus butler when you're accessing catalogs? We do recommend the butler for images when you're in the notebook aspect. The formats are more seamless. When it comes to catalogs, it's not so much size as what you want. When you want like everything in a catalog that's for a given tract or for a given image, The Butler can be better because that's how Butler data is stored. It's stored like by image. So when you just want everything, or if you want an entire column, because the Butler catalogs are also column oriented. So when you want like all columns for all objects or sources, like in a given patch or tract, the Butler is more natural. That's how the data is stored. And then TAP, when you want to put constraints on the columns, like I want everything in this region that's brighter than this, or I want everything in this region that's like red or something like that, then you have to use TAP. TAP is the only way to put constraints on the other columns. So yeah, it's not so much size as what you're trying to do.
Thanks. So I will just wrap up here. Here is just showing the same like mean and minimum and maximum flux that we got from earlier. But yeah, so we've reached I guess the time for the break. We'll have the next session in about 10 minutes, but if anyone has any other questions about the notebook tutorial. Yes, well, you could also, I believe you could also in your query create a column where you convert flux to magnitude and then query on that magnitude. But in the way that I wrote these queries are written, you would have to give it as a flux. But I'll stop.
The object table at least has pre-computed magnitudes already, so you could do magnitude cuts on the object table, but the most of the other tables don't have magnitudes pre-computed, but there is a function that you can use in in ADQL that will actually do the conversion. That's exactly it. It's called SQL flux to, what is it?
AB
Anyway,
math.
we can look up exact function name. Yeah, and it'll convert the magnitudes, and so you can use that to actually cut on magnitude values. Because like you, I am not used to thinking in flux, as most of us are not.